Previously we looked at the structure of the atom. Now we'll go into a bit more detail about the structure of the nucleus. In this presentation we'll look at the composition of nuclei, forces between nucleons, isotopes, and mass defect and binding energy. It's interesting to note that the atom is very small, and because of this it is very difficult to observe. It has only been in the last 100 years or so where the atom has been investigated due to the advancements in technology and science. The main components of an atom include protons, neutrons, and electrons. The protons and neutrons are found inside the nucleus of the atom, and we can label these as nucleons, referring to either the proton or the neutron. This first link that I've provided on this slide is a simulation of an atom, and you can build your own atoms to determine what makes them stable, what makes them neutral, and what makes them different from other elements. The second link is linked to a dynamic periodic table, which provides a lot of information that we're not necessarily interested in this topic. However, information that we are interested in on the periodic table are the atomic number and mass number of an element. So for example, we've got carbon in the big diagram on this page. So the lower number is the atomic number, and this can be denoted either above or below the letter. However, it's always the lower number, and this refers to the number of protons in the element. Now the larger number refers to the mass number, which is the protons plus the neutrons. Now it's interesting to note that this number in most cases is not an exact round number. In this case of carbon is 12.011. Now what that means is it's an average of all the carbon isotopes that are found naturally in nature. So say 96% of the carbon might have 12 neutrons, but however there is a percentage that has a greater number of neutrons that is found naturally. So what the scientists have done is found an average of the isotopes of carbon. Isotopes are different versions of an atom of an element. Every atom in an element has the same number of protons. That's what defines it as that particular element. However, an isotope of the atom has a different number of neutrons. So looking at our example of hydrogen, every hydrogen atom has one proton. Now, an isotope of hydrogen might either have 0, 1, or 2 neutrons. Now you might have wondered why all the positively charged protons inside a nucleus don't repel away from each other. In a very large nucleus, the electrostatic force of all these protons can be very big, and the nucleus should explode. But the reason this doesn't happen is because there's a secondary stronger force called the strong nuclear force that holds the nucleus together. Now the strong nuclear force acts between all particles in the nucleus. So it acts proton to proton, neutron to neutron, and proton to neutron. Now this strong nuclear force can overcome the electrostatic force at close distances. The strong nucleon force acts at a very short range, up to a distance of 1 nucleon. Beyond this, it is effectively zero. At very short range, the force is actually repulsive, which keeps the nucleons separate. Although the strong nuclear force is very strong, if there are a large number of protons in a nucleus, the electrostatic force of repulsion can overcome the attractive force due to the strong nuclear force. This is when an atom becomes unstable. Atoms that have a number of protons over 83 are found to be unstable. Now we're going to get to the interesting bit and talk about the mass defect energy. Okay, in all facets of science, the most stable form is the lowest energy form. And you can compare this to dropping a ball in the field of gravity, where the lowest energy is when it's resting on the ground. Okay, it has been found by experiment that the total mass of a nucleus is always less than the sum of its components. In addition, the total energy of a nucleus is less than the combined energy of separate nucleons. What this means is that a nucleus is actually a lower energy and it's in a more stable form than the individual components. So it has been found experimentally that a helium nucleus, for example, has a mass given in the question there, and the total mass of its individual components is given here. So this leaves a total mass defect, or a change in mass, given in the final line. So where did this come from? The change in mass of a nucleus compared to its component parts can be related to the parts being in a lower energy form when they form the nucleus. And this is given by the equation E equals mc squared. So E represents the energy measured in joules, m is the mass in kilograms, and c represents the speed of light in meters per second. When we discuss mass defect energy, we're talking about the individual components of a nucleus forming together to form that nucleus, and the mass being less when that nucleus is formed. The mass binding energy is when we have a nucleus and the individual components are split, and we actually get a gain in mass. Now, using the equation that we saw before, E equals mc squared, we notice that by even just the smallest amount of mass lost or gained, which is what we're talking about when we're talking about nucleons, the amount of energy that is created is in the order of 1 million times that of a chemical reaction. Looking at the diagram that we've got here, we have individual components of a nucleus being the proton and the neutron. If they join together, they form a nucleus. There's actually a loss in mass, and this mass is released as energy. So the amount of energy that's created is released as a photon, and the energy of this photon is equal to mc squared. Now, chemical reactions produce photons that have energy in the UV range, but the energy in the case of the nuclear reactions that we're talking about here are in the gamma range, which is extremely high energies. Now, when a photon of extremely high energy is impacted upon a nucleus, it can release the nucleons. Now, the energy of that photon is converted to the mass of those individual components, the mass difference. So remember that a nucleus has a lower mass than individual components. So that's why when it is broken up, that additional mass has to come from somewhere, and it's the energy of that photon.